Hello and welcome to this lecture. This is the last week of this class recording, and we've seen quite a bit of interesting ideas on how to study vector spaces, how to study linear maps, right? So linear maps form a huge part of the entire area, and the more we study it, the better off it is, right? The better off we are in understanding. So we saw, for instance, eigenvalues played a very important role in the study of linear maps, right? So they gave you one-dimensional subspaces which are invariant, and that gave you a pretty good idea of what a linear map is. In particular, if you had enough of these one-dimensional invariant subspaces, if your operator became diagonalizable, then there was a very simple diagonal form in an eigenvector basis. And we saw special type of operators like self-adjoint normal operators for whom there's an orthonormal basis of eigenvectors. So those operators are very special because they become diagonal over an orthonormal basis. Now there is an equally powerful idea with huge applications today, which is not based on eigenvalues. It's based on something called singular values and singular vectors. So like you had eigenvalues and eigenvectors, it's possible to define a notion called singular values and singular vectors for, in fact, the general linear maps, right? So we saw eigenvalues, eigenvectors are for operators, right? And now one can define these singular values and singular vectors, and these singular vectors always end up being orthonormal. That's very nice. And singular values always end up being non-negative, and they are there for anything, for linear maps, any map, whether it's from V to W or operator V to V. You can define all that. So it's a different way of looking at a linear map, right? So eigenvalues and eigenvectors tell you, one-dimensional invariant subspaces. That's one way of analyzing it. The singular values, singular vectors are another way of looking at it. You'll see it's very interesting and very surprising how simple and elegant these singular values and singular vectors are, and we'll do that. In the first lecture, I'll simply introduce what is a singular value, what is a singular vector. We won't prove some important results. We'll do that in the subsequent lecture. But it's important to get a feel for what it is and what is the difference between this and eigenvalues, eigenvectors, and see some comparisons. So we'll do that in this lecture. So let's get started. There's a quick recap of all that we've done so far. It's nice when the entire course is recapped into one page. You feel like you've got a good sense of what's going on. So we've been looking at vector spaces over real or complex field. We saw how a linear map has a matrix representation, the fundamental theorem of linear maps, which is dimension of null plus range equals dimension of V. It's very important. We solved linear equations using the null space idea, found all solutions for it. Then these four fundamental subspaces of a matrix give you an idea of how to think of the linear map and all that. And then the important idea of eigenvalue and eigenvector. So in particular, if the matrix can become diagonal with respect to an eigenvector basis, then things are really simple, particularly with respect to powers of the matrix, right? So powers of the operator. So it's just very useful to have the eigenvalue, eigenvector notion. And then we saw inner products and orthogonality, orthonormal basis. This orthonormality simplified a lot of things for us, including basis representation and all that. And then the important idea of adjoint, and how this adjoint is sort of preserves, tells you how inner products work along with linear maps in a very clean way. In particular, that led us to these wonderful operators called self-adjoint and normal operators, which have orthonormal eigenvector basis. Okay, so that's very powerful and strong. And then we saw special cases, more special cases called positive operators, and in fact even more special cases called isometries. These are special type of normal self-adjoint operators, and they have their connections to quadratic forms and all that, particularly the positive operators. Isometries, we'll see some connections today, maybe not today, in these singular values and singular vectors. Isometries will play some role. We'll see some interesting ideas from that. Okay, so this is a quick recap. Let's jump into singular values. Okay, so here's the definition of a singular value of a linear map. Okay, so let's take a linear map T from V to W, vector space V to vector space W. The singular values of T are simply the eigenvalues of square root of T star T. Okay, so that's a pretty big operator written in a very compact way. Square root of T star T. Okay, so T star is the adjoint of T, and this is the square root. So this is I mean, quite a few interesting properties in just this definition. It's an easy enough definition, but quite a few interesting properties. First property is this is a properly well-defined thing. I mean, it's not something wrong. T star T from V to V is a self-adjoint positive operator. Positive is only for self-adjoint, so we know that's okay. So square root and all exists. But before that, let's just use the spectral theorem. When you use the spectral theorem, you're going to be able to write T star T over this suitable basis in this very simple form, right? Lambda 1 E1 transpose E1 conjugate plus lambda n conjugate transpose. Okay, and these eigenvalues are positive, non-negative, so you can sequence them in decreasing order like that. And then this E1 to En is an orthonormal basis, n is the dimension, all that. So we know this is true. From here we can define the unique positive square root of T star T. I never in the lectures proved the uniqueness of this. There is a proof in your book. You can go take a look. It's a unique square root. So we'll pick up the unique positive square root of T star T, which would have the basis representation in matrix representation written in this form. So wherever you have lambda, you put square root. Okay, so everything else remains the same. So the singular values of T in this written down in this way are simply the square root of lambda 1, and that would fall in decreasing order, go all the way to square root of lambda n. Okay. So this is a picture of how singular values are defined. We'll see soon enough couple of examples in this lecture itself. It will be clear to you how this works, but this is the definition, and this definition makes sense. Okay. So why is it that singular values describe T? Okay. So it looks like singular values are numbers related to some other maybe operator square root of T star T, right? So why should that be connected to T? It turns out there is a very strong connection. We will prove it eventually in the next lecture or so, but in this lecture I'll simply illustrate that connection with some examples. Okay, but anyway, I mean, you can also imagine why this T and T star. I've been hinting at how T and T star are sort of the same. So when you take square root of T star T, you sort of expect something similar to T in some sense, right? So a very rough high level picture, but that's sort of the reason why this T and square root of T star T, they have a sort of an intimate connection, which we will establish later on. But for now, it's not surprising that these two are related. Okay, that's that for now. We'll pick it up later. Okay, so what about singular vectors of a linear map? And these are also very easy to define once you know the singular values, and when you see this T star T connection, you'll see that it's easy to define. You once again have a linear map T from V to W. You can define T star T, which will be from V to V. It's a self-adjoint operator. The right singular vectors of T, what I call as right singular vectors, these are simply an orthonormal eigenvector basis for T star T. Okay, so you pick whatever orthonormal eigenvector basis you want for T star T, those would be called as right singular vectors. So it's sort of a easy definition in some sense. Singular values are eigenvalues. Singular vectors are simply the corresponding eigenvectors, right? But not the square root and T star T are okay, right? T star T and square root T star T have the same same sort of eigenvector basis in some sense, right? So it's okay to define it with T star T in this case. Okay, so remember, right singular vectors are vectors in V. Okay, so that's something important to remember. So now you can see where the left singular vectors will come from. Instead of T star T, you look at T star. Okay, remember, T star T is self-adjoint. The adjoint of T star T is T star T itself. So T star is the different other thing, right? So if T were an operator and T were normal, T star and T star T will be the same, but they need not be the same. Okay, T star and T star T can be different. But of course, if it is a linear map, general linear map, with V and W being different, then T star and T star T can have no chance of being the same, right? So because T star T is from V to V, T star is from W to W. But once again, it's a self-adjoint operator. So I can meaningfully think of orthonormal basis of eigenvectors. So if I take an orthonormal basis of eigenvectors of T star, I end up getting what are called left singular vectors of T. Okay, so this is the definition. Once again, right singular vectors are vectors in V, left singular vectors are vectors in W. They are always orthonormal. Okay, by definition, they are orthonormal. There's no, they cannot be anything else, and very easy to come up with. Okay, so even for a linear map T, when V and W are different, these singular vectors are very well defined. They end up being orthonormal basis vectors of V and W related to T star T and T T star. Okay, so simple definition for singular values and singular vectors. Let us see a couple of illustrations and computations and see some surprising properties which we will eventually prove later on. Okay. So, the simplest example is this 2 by 2, and I have been doing this 1, 2, 3, 4 throughout this course. So, we can pick up the 1, 2, 3, 4 again. Okay. So, you have a matrix A 2 by 2 which is 1, 1, 2, 3, 4, let us say standard basis. Okay. That is an easy thing to start with. Okay. We know that this matrix itself has eigenvalues and eigenvectors. You can compute the eigenvalues and eigenvectors. I have done them. I have done that here. So, you see that you get two distinct eigenvalues 5.372 minus 0.372. That is what it seems like. I have calculated it. I have also calculated the eigenvectors. That is one eigenvector is 0.415, 0.909. The other eigenvector is 0.824 minus 0.566. So, these are linearly independent, these two eigenvectors, but they are not orthogonal. You can multiply and check that it will not work out to be orthogonal. So, non-orthogonal to be expected, right. A is not a symmetric matrix. So, you will have a non-orthogonal set of eigenvectors. So, what is the property of eigenvectors? You can check this property. So, the matrix itself A multiplied by the eigenvector is going to give you eigenvalue times the same vector. You can check that this is true, right. So, it is easy enough to see. So, this is the structure of the eigenvalue eigenvector. Now, I want to contrast this with the singular value singular vector picture. Okay. So, this picture itself is quite useful. We have seen that it helps you. So, in fact, you can write A as S inverse ds. Okay. You can write with these exact eigenvectors, you know how to form the S matrix, and A will become S inverse A ds, right. So, D becomes diagonal, and so it's useful. This eigenvector eigenvalue representation is very useful even for this matrix. So, now let us see how the singular values singular vectors look. Okay. So, we know we have to do A transpose A and A transpose to go to the singular value singular vectors. If you do A transpose A, you will get a symmetric matrix 10, 14, 14, 20, you can verify that. A transpose ends up being 5, 25, 11, 11. I hope this is correct. Not made a mistake here, hopefully. A transpose, yeah, it looks okay. Okay, all right. So, I was just checking to make sure, yeah, I think it's okay. So, it's 5, 11, 11, 25, okay, even if there is some mistake, it's okay, illustration is more important, okay. So, the eigenvalues of A transpose A and A transpose, okay, we know that this is ABBA, right. So, the eigenvalues, we know all the non-zero eigenvalues have to be exactly the same. There can be more zero eigenvalues depending on the dimensions of A transpose A and A transpose. In this case, both of them are same dimension 2 by 2. So, the eigenvalues will end up being exactly the same. So, you do A transpose A transpose, you will get the same eigenvalues 29.866 and 0.134. So, this is a trick you should keep in mind. So, sometimes if A and A transpose are not of the same size, A transpose A might be much smaller than A transpose. So, when you want to find eigenvalues, you should be smart enough to go pick the smaller one and try to find it. Okay, so that is something useful, but this is easy enough to see. Okay. So, once you have the eigenvalues of say A transpose A, I can find the singular values. Singular values is simply the square root of the eigenvalues. So, you take square root of 29.866, you get 5.465, square root of 0.53134, you get 0.366. So, that is the singular value. It is typical to denote singular value with this sigma, okay, sigma 1, sigma 2 in that sequence, sigma 1 greater than or equal to sigma 2, etc. Okay. One can also find right singular eigenvectors and left singular eigenvectors, okay, for these two eigenvalues. In this case, it is all unique and all that. So, you will get the same answer. You may change up to sign, but only up to sign you can change, everything else will work out. And it is very typical to write right singular eigenvectors, left singular eigenvectors as orthonormal basis. Okay. So, you can see E1 and E2 is an orthonormal basis for 2-dimensional R2, and similarly F1 and F2 is also orthonormal basis. Okay. E1 and E2 are eigenvectors of A transpose A, F1 and F2 are eigenvectors of A transpose. Okay. So, these are calculations you can check. I am not going to go through great detail for you. You can check that these are true. Okay. So, you see eigenvalues were defined in one way, you know how to calculate them. Singular values and singular vectors are ending up in another way. I know that eigenvalues gave me the, you know, S inverse AS, S inverse DS type transformation for A, representation for A, and that helped me in so many ways. What is going to happen here? Okay. So, we will see what it does eventually, but let us look at something very interesting. So, when the matrix operates on the eigenvector, you expect something very simple in terms of the eigenvalue and itself, right. So, what happens when the same matrix A operates on the right singular vector, right. So, let us pick the right singular vectors and say the matrix A operates on them. Look at what happens, some magic will happen here. So, you take A and multiply by the right singular vector, the first one here E1, end up, notice what you are getting, you will get sigma 1, the singular value multiplying F1, okay. And if you take A and multiply, multiply on the right with E2, right, AE2, the second right singular vector, you end up getting the second singular value multiplying the second left singular vector, okay. So, these kind of properties, this is not an accident, AE1 is sigma 1 F1 and AE2 is sigma 2 F2. This is the defining property for singular vectors and singular values. Just like you have, you know, AX equals lambda x, maybe I should write that alone. So, AX equals lambda x is sort of the defining property for eigenvalues definition. This is the defining property for singular value, singular vector definition. Okay, so you have always orthogonal. So here you have two eigenvectors, they're not orthogonal. Here the singular vectors are always orthogonal. And then what happens to singular vectors when A operates on them? They go to orthogonal vectors as a result, right? The output is still an orthogonal set of vectors. These two are orthogonal. They are scaled by the singular values, and that's it, right. So, it's not like it's invariant, the singular vectors are not invariant, but they sort of provide a very nice and complete picture of what A is, okay. They take an orthonormal basis to an orthonormal basis in some sense, right. So, that's the crucial idea. We will prove this eventually in the next lecture or so, we will prove this result, and this is the essential aspect of right and left singular vectors and singular values, okay. So, it is important to understand. This is one example, okay. Hopefully, this was clear. Let us see one more example just to drive home the point of how singular values and singular vectors work, and this time I will take a non-square example, 2 by 3, okay. So, if you take 2 by 3, then there is no question of eigenvalues or anything, right. So, those things do not make sense. So, we have to go to singular values. When we go to singular values, let us look at A transpose A and AA transpose. Okay, so here you see the difference, right. A transpose A is 3 by 3, AA transpose is just 2 by 2, and you can look at eigenvalues of A transpose A, you will get some number 90 and some 0.5. Eigenvalues of AA transpose, we know what it will be, right. It will be the two non-zero ones will be the same, the 0 will drop out, right, that is what will happen. So, the singular values of A are in fact the eigenvalues of A transpose A. So, it is common, so you can take square root of the eigenvalues of A transpose A. So, you get 9.5, 0.773, and then the sigma 3 is 0, okay. So, you get that. And you can find right singular vectors of A, these will be the eigenvectors of A transpose A, you will get E1, E2, E3, and once again E1, E2, E3 is a orthonormal basis for R3, okay. So, that is V R3, that is V to W, right. A is from V to W, V is R3, W is R2. So, E1, E2, E3 is an orthonormal basis for R3, okay. So, this corresponds to the eigenvectors of A transpose A, the orthonormal basis eigenvectors of A transpose A. Similarly, you can also find left singular values of A. Now, this will be now left singular vectors of A, I am sorry. These will now be an orthonormal basis for R2, okay. So, this is different, right, the range is in a different vector space, but still the orthonormality will be satisfied, okay. So, this is sort of gives you an idea of how it works. So, even when eigenvalues are not properly defined, you can say something with singular values, okay. So, again you test this little result that we have. AE1 is again sigma 1 F1, AE2 is sigma 2 F2, AE3 is 0. Okay. So you notice what's going on here. So there is an orthonormal basis which transforms through A to another orthonormal basis, and the singular values are the scaling factors that come in the middle. Okay. So this is a very powerful description for any linear map. So is it true for any matrix? Okay. So these are the questions we have to ask. We'll ask this and we'll answer these questions in the next lecture, but in this lecture, this hope you see the magic of what's going on. So we are able to find an orthonormal basis which, when hit with a matrix A, takes you to an orthonormal basis. That ends up being the huge simplification here, and it's all connected to this A transpose A and A transpose and its eigenvalues and eigenvectors. Okay, so hopefully these two examples gave you a feel for how to work with singular values and singular vectors. And always remember this A transpose A transpose, one of these will be smaller. Okay, so you should just go there, go to that, and then go to the smaller one, and then work with that. Okay, so work with that eigenvalue and those eigenvectors, and then F1 and E1 you can find through these relationships, right? So it's all easy to sort of do. You don't have to do a lot of work for these small size problems. But of course, today SVD is the heart and soul of any numerical implementation of linear algebra. In fact, all problems, any linear algebra thing that you ask a computer program to do with a matrix, it will first find SVD. Okay, and all answers about the linear map can be given from the SVD. Okay, so you'll see why. I mean, we will see later on in more detail why this SVD is so powerful. Singular value decomposition and singular values and singular vectors are so powerful, and they give you a very succinct, clean, nice description of any linear map. Okay, so this is just a numerical illustration. At this point, we'll see more proofs and more properties later on. Okay, so at the heart of all of this is this all sorts of connections between null space, range space of T, T star, T star T, square root T star T, and T T star. Okay, so these are all the various things that are going on here, and they are from various spaces to other. That's written down here, and their nulls and ranges are all strongly coupled and connected, right? And we've seen how to work with these before. There are a whole bunch of results we saw on what happens when you multiply two operators, right? When you compose two operators, how do you think of the null space of that and all that? But you know, T and T star have a very special connection, so you can use that and then simplify all the properties. So I'm going to write down 4 different properties. They may be a little bit confusing, but think about them clearly. You will get a good idea, and that is very critical in our proofs and other things that we do. Okay, so this is important to understand. So the first is T and T star. This is standard, right? So any T and T star, null T is range T star orthogonal complement. Okay, and the same thing with T star. Instead of T, if you put T star, you will get null T star is range T orthogonal complement. And from this, you can conclude that range of T and range of T star have the same dimension. Okay, this is true for any operator T. We know that this is true, right? So once you have something like this, it turns out, see, null of T star, null of T is range of T star. So if you look at T star T, right, the only way to get the null of thing is to make T itself null. Because why? Because range of T and null of T star have a trivial intersection, right? So range of T and null of T star are actually orthogonal complements, so they don't intersect at all. So the null of T star T is going to be equal to null of T. So this is a crucial relationship. So because of this, range of T star T, which will have to be null T star T orthogonal complement, right? This, why is this true, by the way? The first part, why is this true? This is true because T star T is self-adjoint. Okay, so T star T is self-adjoint. Once you have a self-adjoint operator, its range is the orthogonal complement of its null. Now, what is null T star T? It's the same as null T. So null T perp. What is null T perp from here? Range T star. Okay. So range T star T and range T star are exactly the same. Okay. All right. They are equal. There's no difference here. Okay. It's not just dimension or anything. They are actually equal. Now, if you look at dimension, so dimension of range T star T becomes dimension of range T star, and that is equal to the dimension of range T also. Okay. So in dimension, all of these things are the same. So it adds to my notion that, you know, T star and T star, T star, T star, a lot of these important properties, and that's why it's interesting to look at them. Okay. All right. So this is the second one. Let's go to the third one, which talks about square root of T star T. So now if you look at the square root of t star t, how do you sort of see this? So you see that, you know, t star t equals square root of t star t times square root of t star t. Now all these are self-adjoint, right? So these two are both self-adjoint. So what will happen? The range of t star t and null of square root of t star t will be orthogonal complements, right? So at this point, if you see, null of square root of t star t is the range of square root of t star t perpendicular. Okay, so because of this, right, the only way to make t star t null is to also have square root of t star t null going to the null space, right. So because the range of this and the null of the next one have no intersection, have a trivial intersection. Okay, so that's why null of square root of t star t, because of the self-adjoint property, is equal to null of t star t, and null of t star t is the same as null of t. Okay, so range is also the same, right. So dimension means same in the sense, you know, very similar description to before. So dimension of range of square root of t star t is also equal to dimension of range of t. Okay, so this is important to know. Okay, so t star t, square root of t star t, all of them have the same range dimensions. Okay, and this will be useful for us later on. Okay, so hopefully that gave you a clear idea. So finally, what about t star? So far I have been talking about t star t. If you want to do t star, simply take any of these relationships, and instead of t, you replace with t star, right. So that is the idea, you do that. So how do you get from here to here, for instance? Put t equals t star. Okay, so you replace t with t star, you will get null of t star is null of t star, and that is range of t star perpendicular, right. So null and range are the same. So range t star is null of t star perp, and that is range t. Okay, so this is also important. Range t star t star is range t. Okay, so just like we had here, right, range of t star is the same as range of t. Okay, so if you want more pictures, so let us say this is V and this is W, t takes you from here to here, t star takes you from here to here. So range of t will be somewhere here, right. So this is range of t, let us say. What is t star and then t? So if you take t star and then t, okay, so you will have a range of t star here. So these two have the same dimensions. Maybe I did not draw it correctly. Maybe I should do that, cut it short a little bit so that they have the same dimension. These two have the same dimension. So if you do this t star and then t, you go back to the same range. Okay, so the range of t star t is the same as range of t. Okay, and then look at square root of t star t. Okay, so if you look at range of square root of t star t, so you have null t, right, null t. Okay, so null t. Okay, null t and range t star are orthogonal complements, so they allow only a trivial intersection, right, null t, and null t is the same as null of square root of t star t. Okay, so the square root of t star t is both of these are same, and you know, right. So null is the same. So if you want to look at the range, you will end up getting the range of t star, right. So if you take the orthogonal complement of this, so range of t star is the same as range of square root of t star, right. Range of t star is the same as range of t star t is the same as range of square root of t star t. Okay, all of these have the same range. You can also write similar expressions for range of t and range of t star. Okay, so they all have the same range, they all have the same null. Okay, so this is also equal to null of t star t. Okay, so hopefully you see the picture. These are two orthogonal complements and they all are the same. Okay, so as far as sizes and everything is concerned, they are the same, the dimensions are the same. Okay, and they also have more intricate connection, particularly the square root. I will show a very close and intricate connection in the next slide, and that will give you what's called the singular value decomposition, and that's very powerful. And finally, it will connect all that we've been seeing as illustrations in this class. Okay, so hopefully this slide was maybe a little bit confusing, but it's sort of important to know how all these null spaces and range spaces are very directly and closely connected in terms of just being equal and dimensions being same and all that. Okay, so I'll stop here. We saw 2 or 3 nice illustrations of how to compute singular values, how to compute left singular vectors, right singular vectors, and that wonderful relationship between them. Okay, A times right singular vector is singular value times a left singular vector. Okay, so that's a very critical relationship, and singular vectors are always orthonormal, and that will lead us to what's called singular value decomposition and polar decomposition, and we'll see that in the next lecture. Thank you very much.